The first and most obvious challenge is, without question, the sheer scale of the distances involved. So, let's consider our closest stellar neighbor. It's a star called Proxima Centauri, and it sits approximately 25 light years from Earth. To grasp what that figure truly represents, think about this. Light, the fastest thing in the entire universe, requires over 4 years to complete that single journey. 4 years! And that's just the nearest star. The vast majority of those twinkling points of light in the night sky are situated at distances that dwarf that. Some are situated hundreds of light years away. Take Sirius, for instance, one of the brightest objects in our sky. It's roughly 85 light years distant. Now, your initial reaction might be, okay, it's a long way, but we've made it to the moon, and we've sent probes to Mars. Eventually, we'll just scale up and make the leap to another star. I completely understand that line of reasoning. However, I need to illustrate why this isn't merely a larger scale version of the same challenge. This is an entirely different category of problem. When we contemplate travel within our own solar system, heading to Mars or even Jupiter, we're talking about distances that, while vast, are still within our frame of reference. The travel times are lengthy, certainly, but we measure them in months or perhaps a handful of years. But once you cross into interstellar space, the time scale shifts to decades, centuries, or even far longer. This introduces obstacles that aren't just about engineering. They're fundamental problems rooted in physics. The most significant of these, the one that presents an absolute barrier if you really stop to consider it, is the speed of light. Einstein demonstrated, and experiments have verified this time and again, that it's impossible for any physical object to exceed the speed of light. Not faster. Full stop. This isn't a matter of our rocket engines lacking sufficient power. It isn't a technology we haven't invented yet. This restriction is woven into the very fabric of space and time. It's a deep-seated rule of the universe, and you cannot circumvent it through clever thinking or by constructing larger machines. So, if a photon takes 4 years to reach Proxima Centauri, the absolute minimum time for a spaceship to make the same trip is also 4 years. That's the best-case scenario, and it assumes we can travel at light speed, which we cannot. In reality, we would have to travel far slower. At this point, a logical question arises. Why can't we simply build a ship that goes incredibly fast? Why couldn't we achieve 90% of light speed or 95%? The answer boils down to one word: energy. An almost incomprehensible amount of it. Let me break this down. Imagine you're piloting a spacecraft and you want to accelerate to a certain velocity. Let's say your goal is to hit 10% of the speed of light, which is roughly 30,000 kilometers per second. To get any object moving that fast, you have to impart kinetic energy to it. The higher your target speed, the more energy is required. But here's the crucial part. As you inch closer to the speed of light, the energy demands don't just increase steadily, they skyrocket exponentially. It becomes progressively more difficult the faster you try to go. The formula that governs this comes from Einstein's theory of relativity. It tells us that the energy needed to increase your speed grows immensely as you approach the cosmic limit. By the time you're at 90% of light speed, you're already dealing with a colossal energy requirement. At 95%, it's even more staggering. And at 99%, the figure becomes almost beyond imagination. Let's ground this with some specific figures so you can appreciate the scale. Suppose you wanted to accelerate a payload of just 1 metric ton, a tiny fraction of what a real starship would weigh to 10% of light speed. The energy required would be equivalent to the explosive power of several megatons of TNT. Several megatons. And again, that's for a single ton just to reach 10% of light speed. If your goal was to get a more realistic ship, say one weighing 1,000 tons, up to 50% of light speed, you'd be looking at energy on par with millions of megatons of TNT. So, where could we possibly get that kind of power? One concept that's been proposed is antimatter propulsion. When antimatter meets ordinary matter, they annihilate, converting their entire mass into pure energy, perfectly described by Einstein's famous equation, E equals mc squared. In theory, this is the most efficient fuel source imaginable. If we could manufacture and safely store antimatter, it would provide more energy per unit of mass than anything else we know. But here's the immense hurdle. We are incapable of producing antimatter in any meaningful quantity. We can create a few atoms in massive particle accelerators, but the sheer volume we're talking about, The amount needed to fuel an interstellar vessel is utterly beyond our present capabilities. And I mean utterly. This isn't something we're likely to achieve in the next 50 years. Perhaps we could manage it in the distant future, but we currently have no roadmap for how to get there. It's not just an engineering hurdle, there are profound physics questions about how you would even contain that much antimatter safely. And even if we solve the production and storage, there's another catch. Not all the energy from the annihilation goes into pushing the ship forward. A significant portion is lost as stray radiation, as particles spraying off in random directions, and as waste heat. So the real-world efficiency would be far lower than the theoretical ideal. There's another fundamental problem I need to discuss, and it's a critical one. It concerns what happens when you move at extreme speeds through the cosmos. You see, space is not truly empty. We tend to picture it as a perfect void, a pristine vacuum, but that picture is inaccurate. Interstellar space is filled with the thin gas atoms of hydrogen, helium, and other elements scattered about. It also contains dust, microscopic grains of solid matter, and it's permeated by cosmic rays, high-energy particles racing in from all corners of the universe. When you're moving slowly, these things are negligible. An occasional atom bumping into your ship is irrelevant. But when you're traveling at a substantial fraction of the speed of light, say 30% or more, something very strange and incredibly dangerous begins to happen. From the perspective of the spaceship, due to relativity, it's not the ship that's moving, it's the entire universe that's rushing toward it. And when those particles strike you at these relativistic speeds, they carry an immense amount of kinetic energy. Remember that exponential curve for the energy required to accelerate? The same principle applies in reverse here. A single hydrogen atom hitting your ship at 50% of light speed possesses far more kinetic energy than classical physics would predict. It's effectively transformed into hard, ionizing radiation. What this means in practice is that as your ship plows through the interstellar medium, it's being constantly pelted by this relativistic wind of particles. These impacts are stripping electrons from atoms, creating a shower of ions. If a person were unprotected inside that ship, they would receive a lethal dose of radiation not in minutes, but in seconds. And it gets worse. Those tiny dust grains, I mentioned minuscule specks of solid material, become terrifying projectiles. When one of them strikes a ship traveling at 30%, 40%, or 50% of light speed, the impact is like being hit by a high-velocity bullet. A microscopic grain becomes a devastating projectile with enough energy to punch clean through the hull. You could, in theory, protect against this by placing shields at the front of the ship, but shields have mass. And when your primary goal is to reach incredibly high speeds, mass is your worst enemy. You have to accelerate every kilogram of that shielding along with you, and accelerating more mass requires even more energy. It's a brutal trade-off. You can shield yourself, but it comes at a tremendous cost in terms of the fuel and power needed. There's also a fascinating perceptual shift. As your speed climbs and you approach the speed of light, the very appearance of the universe changes. Light from all directions gets concentrated into a narrow cone ahead of you. This is known as the beaming effect, related to relativistic aberration. At extremely high speeds, virtually all the visible light from stars and galaxies gets focused into a small circle directly in front of your ship. You'd be looking out of the cosmos through a constricted tunnel. The universe would appear as a bright point of light ahead, with nothing but darkness to the sides and behind. It's a bizarre consequence, but it's a real one according to physics. Now, I want to address a concept people sometimes bring up, often because it reflects a misunderstanding of the physics involved. They'll ask, what about time dilation? Couldn't that get around the speed limit? Time dilation is absolutely real. Einstein showed that if you travel at extremely high speeds, time passes more slowly for you relative to a stationary observer. If you journeyed to Proxima Centauri at 95% of light speed, you might personally experience only a few years passing while decades slip by back on Earth. That's a genuine effect, a proven consequence of relativity. But here's the essential point. Time dilation does not help you go faster. It doesn't allow you to bypass the speed of light. What it changes is your personal subjective experience of the trip. From Earth's perspective, your journey still takes more than 4 years because you are, by definition, traveling slower than light. You simply experience less of that time personally. So, if you departed Earth in the year 2050, traveling at 95% light speed, you might feel like the trip to Proxima Centauri only took 4 or 5 years. But upon your arrival, the calendar on Earth would read 2100 or later. Everyone you knew would be much older or likely gone. The world would have moved on without you. So, time dilation is a fascinating phenomenon, but it's not a solution to the problem of distance. It's simply a strange side effect of moving at relativistic speeds. Some people have heard of concepts like wormholes or warp drives from science fiction and wonder if these could be the key. They imagine shortcuts through space-time or a way to bend space itself, creating a bubble that could travel faster than light. I want to address this carefully because I don't want to dismiss possibilities in a way that sounds close-minded. Science must always remain open, but I need to clarify the actual status of these ideas. According to Einstein's theory of general relativity, wormholes, sometimes called Einstein-Rosen bridges, are theoretically possible. They emerge as solutions from the equations. In theory, they would act as tunnels connecting two distant points in space-time. If they existed and were traversable, you could, in principle, cross immense cosmic distances almost instantaneously. However, they come with a host of enormous problems. First, we have no evidence whatsoever that wormholes actually exist in our universe. Second, even if they do, we have no idea how to locate one, let alone how to navigate it. Third, and this is critical, theoretical analysis suggests that any such wormhole would be fundamentally unstable. It would collapse in on itself almost instantly. Trying to pass through one would be like trying to jump through a door that's slamming shut at the exact moment you reach it. And fourth, we're back to the energy problem. The calculations indicate that creating a stable, traversable wormhole would require access to exotic matter with negative energy, and in quantities that are simply mind-boggling. We're talking about energies on the order of the Planck energy, which is quadrillions of times greater than what our most powerful particle accelerators can produce. So, as fascinating as they are mathematically, wormholes offer no practical path to interstellar travel. What about warp drives? The idea of warping space-time around a vessel to allow faster-than-light motion is even more speculative. There are solutions to Einstein's field equations, the most famous being the Alcubierre metric, that appear to describe something like this. But the problems are even more severe than with wormholes. Again, you'd need exotic matter and astronomical amounts of energy, and frankly, we don't even know if the concept is physically realizable at all. It's entirely possible that while general relativity permits these mathematical solutions, the universe simply does not allow them to manifest in reality. And here's a crucial point. Even if a warp drive were somehow possible, it would almost certainly violate causality. It would open the door to time travel, bringing with it a host of paradoxes and logical contradictions. The universe seems to have safeguards against this, a kind of chronology protection that prevents such violations. Nature appears to forbid things that would create logical absurdities. So you might be thinking, okay, maybe faster than light is out. But what if we simply accept that interstellar travel will take a very long time? What if we build generation ships? This is the concept of a world ship, a massive vessel where people are born, live their entire lives, and die with their descendants eventually reaching the destination. Within the constraints of known physics, this is arguably the most plausible approach. You construct an enormous spacecraft, a self-sustaining miniature world. Over centuries or even millennia, it slowly drifts towards another star system. Upon arrival, the crew is composed of the distant descendants of the original voyagers. But even this seemingly more realistic option is fraught with immense challenges. First, building a spacecraft large enough and robust enough to support a human population for hundreds or thousands of years is an engineering challenge of staggering proportions. We have never attempted anything remotely similar. We don't know how to close all the loops for water, air, food, and materials for that length of time. The structure would have to maintain its integrity for centuries while being bombarded by the harsh environment of space. That alone is not a simple problem. However, there's a deeper, more profound challenge, the psychological and sociological one. You are asking generations of people to spend their entire existence on this ship. Their children will be born on it, live on it, and die on it. Their grandchildren will do the same. Everyone they will ever know will share that same confined existence. After dozens of generations, would those people still feel any connection to the original mission? Would they still be motivated to reach a distant star they will never see? Or would they start to question the purpose, wondering why they can't just stop somewhere, or change course, or simply return? These aren't trivial questions. They touch on fundamental aspects of human motivation and society. There's also the critical issue of genetic diversity. The initial population would need to be large enough, likely thousands of individuals, to avoid the pitfalls of inbreeding and genetic disorders over many generations. This would require careful management of reproduction, a concept that quickly veers into dystopian territory. How do you manage that ethically and psychologically? Another idea that often comes up is hibernation or suspended animation. The crew is put into a state of deep sleep for the duration of the journey, waking only upon arrival. Currently, this is far more science fiction than science fact. Let's consider what it would actually entail. First, you need a reliable method to preserve a human body in a state from which it can be revived without damage. We cannot do this today. We barely understand how to do it for small animals. The formation of ice crystals during freezing tears apart cells. We need to develop advanced cryoprotectants to prevent this damage, and then devise a safe and effective rewarming process. This isn't just a technological hurdle. There may be fundamental biological barriers that make it extremely difficult, if not impossible. But for the sake of argument, let's assume we solve that. We're still left with the problem of the journey itself. If the crew is unconscious, the spacecraft must be fully autonomous. It would need to navigate, make course corrections, and handle emergencies entirely on its own for decades or centuries. The required level of reliability is almost unimaginable. And what happens if something goes seriously wrong? What if the ship develops a critical fault and there's no one awake to fix it? Then there are the legal and ethical dimensions. If you place someone in suspended animation, what is your responsibility towards them? What if the revival process fails? What if they wake up in a future world with a completely different set of values and laws than the one they left behind? These are profound questions without easy answers. I want to shift focus now to something I find particularly important, and it gets to the heart of why these discussions are so compelling. I want to explore the distinction between what is theoretically possible and what is practically achievable. There's a tendency in conversations about future tech, a kind of cargo cult approach to science, where people reason like this: Einstein's equations allow for wormholes, therefore wormholes must be possible. Therefore, interstellar travel via wormholes is possible. But that's a fundamental misunderstanding of how physics works. The fact that an equation has a solution that describes something doesn't mean that thing exists in nature. And it certainly doesn't mean we can harness it. Let me offer an analogy. The equations of general relativity also allow for solutions that describe closed, time-like curves, in essence, paths that could allow for time travel. You can write down the math and get a result that looks like it permits time travel. But does that mean time travel is actually possible? We don't know, but there are very good reasons to suspect it is not. Nature seems to have safeguards, what physicists call the chronology protection conjecture, that prevent paradoxes from arising. So even though the mathematics permits it, the universe may forbid it. It's the same with faster-than-light travel. Yes, you can find mathematical solutions that appear to allow it, but does that mean it's physically realizable? All the evidence from observation and experiment suggests it is not. Whenever physicists have scrutinized these solutions to see if they could be used for practical FTL travel, they've uncovered fundamental show-stopping problems. There always seems to be a reason it wouldn't work. And here's another crucial point. Being open-minded to new ideas does not mean uncritically accepting every speculative concept. True scientific honesty requires stating clearly, here's what we know with confidence. Here's what we don't know. Here's what we've tested and found to be false. And here are the constraints that the universe appears to impose. It means making a sincere effort not to fool yourself. I believe we need to confront the difficult truth about interstellar travel. The hard truth is that it is fundamentally limited by the speed of light. Any vessel we could ever build will take many, many years to reach even the closest stars. That basic fact is not going to change, and I think accepting this is actually productive, because it reshapes how we approach the problem. If you accept that interstellar voyages will necessarily be long, then the sensible approaches are the slow ones. You focus on building highly efficient, robust spacecraft that can sustain human life for decades. You grapple seriously with the biological and psychological challenges. You plan for multi-generational missions. These are extraordinarily difficult problems, but they are not necessarily impossible ones. They are problems that humans, given enough time, resources, and dedication, might eventually solve. But if you cling to the hope that some miraculous breakthrough will allow you to exceed light speed, or that some exotic new physics will simply erase the problem, then you are fooling yourself. You are building your hopes on a foundation of sand. Someone might challenge me, but aren't there always new discoveries in physics? Aren't there things we don't yet understand? How can you be so certain? That's a perfectly fair question. Science is, by its nature, always open to revision. But here's the key point. I'm not saying this because I'm personally attached to current theories. I'm saying it because of the overwhelming weight of evidence. Special relativity has been tested and verified thousands of times in countless experiments in particle accelerators, in observations of cosmic rays, in atomic and nuclear physics. Every single test has confirmed its predictions. The speed of light being a universal limit is one of the most robustly established facts in all of science. Could there be some entirely new physics that overturns everything? Well, sure, it's possible in the most abstract sense. But you cannot plan your understanding of reality on the off chance that all the evidence is wrong and that a hidden truth awaits discovery. That's not science, that's fantasy. So, let me try to bring this all together. The idea of interstellar travel is incredibly alluring. We look at the stars and we feel a pull to go and see them. But there are fundamental laws of physics that place hard limits on what's achievable. Nothing can move faster than light. Reaching even a fraction of that speed demands incomprehensible amounts of energy. The interstellar medium itself is a hostile environment for high-speed travel, and we have no realistic path to circumvent these barriers. This doesn't mean interstellar travel is impossible. It means it's constrained. It means it will be slow. It means it will require solving immense engineering problems, as well as enormous biological and sociological challenges. But you know what? If humanity ever does achieve it, if we ever actually send a vessel to another star, I believe it would stand as one of the greatest accomplishments in our history, not just because of the technological marvel it would represent, though that would be staggering, but because of what it would signify, our ability to think in the long term, to plan for centuries or millennia, to dedicate ourselves to a project that we, personally, will never see completed. That's a mode of thinking we rarely engage in. We are typically consumed by short-term problems and immediate gains. Interstellar travel would demand a different kind of vision. It would require saying, yes, this is incredibly hard. Yes, it will take an immense amount of time, but it is worth doing. And I find that vision deeply compelling. I think it's something truly worth aspiring to, even if the physical laws ensure it will always be exceptionally difficult and achingly slow. So, the conclusion, as I see it, is this. Interstellar travel will likely happen eventually. Probably, but it will happen in a way that is very different from our science fiction dreams. It will be slow, it will take a long, long time, and we will need to be incredibly clever and utterly dedicated to make it work. And honestly, I find that reality far more interesting than the fantasy versions with fleets of faster-than-light ships exploring dozens of star systems. Because the real version, the version constrained by the actual laws of physics, is a much harder problem. And harder problems are always the more interesting ones. Thank you.